This video goes over solving trigonometric equations using radians. So just like solving any other equation, we are trying to isolate the variable. This time the variable is being acted on by a trig function. So in order to get rid of that trig function, we're going to really do the inverse operation to the other side. So the first thing that I'm going to do is I'm going to find the location of my possible answers. So my equation tells me that the sine ratio is positive. So that means that my angle could be in the first quadrant or it could be in the second quadrant. So I'm going to have two solutions which are connected by the same related acute angle, which is here in red. So the second thing that I'm going to do is I'm going to find my related acute angle. In order to do that, I'm going to take the sine inverse of the decimal value that is on my right-hand side. I don't need my special triangles here because I don't have an exact value. Once I've found the related acute angle using my calculator, you do need to make sure that your calculator is in radians. Then I'm going to find my solutions in the relevant quadrants. So in quadrant 1, my theta, my first solution, is equal to my related acute angle. So that means my first solution is 0.8408. 0.8406, and in my second quadrant, my solution is pi, take away my related acute angle, which is going to give me an answer of about 2.3 radians. And those are the solutions that if I put those values in for the theta on my left-hand side, my left hand is going to equal 0.7451, the same as the right-hand side. So let's try the second example here, which is a cosine. So the first thing that I'm going to do is find the possible locations using the sign of the ratio. So I'm going to draw my quadrant, label them, and then I notice that my cosine ratio is negative, so that means I'm going to have two solutions. One is in quadrant 2, and one is going to be in quadrant 3. So I've got my first solution, and then I've got my second solution down here, both of which are connected by a related acute angle, which is the same for both cases. So my next step is going to be to find my related acute angle by doing the cosine inverse of the positive value of the angle. So it's almost like I'm pretending the angle is in the first quadrant, and I'm going to do the cosine inverse of that value. This is going to give me a related acute angle of 1.4583. And now I can use that related acute angle to find my solutions. So my first solution in quadrant 2 is going to be pi minus my related acute angle, which is going to give me a value of about 1.6832. And my solution in quadrant 3 is going to give me a value of pi plus my related acute angle. That is always the same for a solution in the third quadrant, which means that my second solution is 4.6 radians. Neither of those two use special triangles. The next ones do. I can identify that I'm going to need an exact answer because that ratio is one of my special triangle ratios, and the question is asking me to give an exact answer. So just because it's exact doesn't mean my values change at all. I'm still going to do the same thing. The first thing that I'm going to do is find my possible locations. And so that means that I need to draw my quadrants. Cosine is positive, so that means I have a solution in the first quadrant, and I have a solution in the fourth quadrant. I know that both of those solutions, so the first one and the second one, are both related by the same related acute angle. In order to find my related acute angle, I am taking the cosine inverse of the right-hand side, is mathematically what I'm doing. But I also know that in my triangle, I know that when my hypotenuse is root 2 and my adjacent side is 1, that matches my special triangle. And I know that that angle is pi over 4. So I can say that exactly, that the cosine inverse of 1 over root 2 is pi over 4, which is my related acute angle, which then means that I can find my solutions in quadrant 1. My solution is equal to the related acute angle, which is pi over 4. And in quadrant 4, my solution is going to be 2 pi take away the related acute angle, which is going to end up giving me 8 pi over 4 minus pi over 4, which is 7 pi over 4. So that's an example of solving, giving an exact answer using special triangles. And we're going to do another example like that. So here I've got a negative value. So the first thing I'm going to do is find my possible locations. Sine is negative. That means I have a solution in the third quadrant and the fourth quadrant. Second thing that I'm going to do is I'm going to find my related acute angle. My related acute angle is the inverse of the positive version. I have also seen those side lengths before. Sine, this is the angle that I'm looking for. Root 3 would be my opposite, 2 would be the hypotenuse, and 1 would be the adjacent. This angle right here that goes with that value is pi over 3. So that means that my related acute angle is pi over 3. Using my special triangle, that gets me an exact value. Now I'm going to find my first solution and my second solution. So in quadrant 3, my solution for the angle for that equation is going to be pi plus my related acute angle, which would give me 4 pi over 3. And in quadrant 4, my solution is going to be 2 pi minus my related acute angle, which would give me 5 pi over 3. The next couple examples involve equations that are a little bit more complicated because they have some simplification that comes along with them. This one here, what I notice is that I've got cosine values on the left and the right side. I want to move all the values that have an x onto the left-hand side, following my BEDMAS rules, and I'm going to move all the terms that don't onto the right-hand side. That means here I've got 3 cosine x on the left and 1 on the right. Isolating cosine x gives me 1 over 3. Because my cosine ratio is positive, I know I have a solution in the first quadrant and in the last quadrant. I'll use x here, x1 and x2. Both of those are connected by the same related acute angle, which I can find by doing the cosine inverse of 1 over 3. Cosine inverse of 1 over 3 gives me approximately 1.23. And my last step is to find my solutions. So in quadrant 1, my solution is just equal to the related acute angle, which is 1.23. And in quadrant 4, my solution is 2 pi take away the related acute angle, which gives me a solution of 5.053. Example 3 involves some more algebra involving cosine functions, but the idea is still to try and isolate x. In order to do that, I'm going to distribute to get rid of the brackets. So I've got 4 cos x minus 8 equals 2 cos x minus 9. Then I'm going to move all the terms that have a cosine onto the left-hand side, and all the terms that don't onto the right-hand side, following my rules for moving terms. This simplifies to 2 cosine x equals minus 1. Isolating cos gives me cosine x equals minus 1 over 2. This is a special triangle ratio. So I'm still going to start by finding the quadrants for my solution. Cosine is negative, which means I've got a solution in the second quadrant and in the fourth quadrant. Here I've got x1 and x2. Both of these are related by the same related acute angle, which is here. My related acute angle I am finding by doing the cosine inverse of the positive version of the ratio. But I know that this is a special triangle. For cosine, this is really the angle that I'm looking for. Cosine is my adjacent side and the hypotenuse, and that makes root 3 my opposite, which means that my related acute angle is pi over 3. Now this is going to let me find my solutions. So my solution in quadrant 2 is pi minus pi over 3, which gives me a final solution of 2 pi over 3. And in quadrant 4, my solution is 2 pi minus pi over 3, which gives me a solution of 5 pi over 3. For cosine, just double checking my signs, my solution should actually be for cosine to be negative. My second solution should actually be in this quadrant right here with my related acute angle right here, which means that my second solution is actually in quadrant 3, which is pi plus my related acute angle, which is going to give me a solution of 4 pi over 3. I can always verify my solutions to equations by doing a left side, right side check, the same way you would for a linear equation. The last example that we're going to do here is we're going to take a look at solving for an equation that has a composite angle in the argument. So this one has x plus pi over 2. And so all I'm going to do first is I'm actually going to get rid of it by using a variable to represent that x plus pi over 2. So that means that my equation is now sine A is equal to 1/2. I know that my sine ratio is positive, so I've got a solution in the first quadrant as well as in the second quadrant. This is my first A value and my second A value. Both are related by the same related acute angle, which I can find by taking the sine inverse of 1 over 2. 1 over 2 is one of my ratios that's on my special triangle. I actually already have it up here. The first one that I did in example 3 was pi over 3 was my related acute angle. I'm actually looking for the opposite angle here because I need my sine ratio to be 1 over 2, which means the opposite side is 1. So this tells me that my related acute angle is pi over 6. Then I can find the location of my solution. And I'm going to say that in quadrant 1, my A value is equal to pi over 6 because it's equal to my related acute angle. But my a value is not actually the x value that I'm looking for. This would be x1 plus pi over 2 is equal to pi over 6, which means that I need to solve for my x value by doing pi over 6, take away pi over 2, which is going to give me a final value of minus 2 pi over 6 or minus pi over 3. In my second quadrant, my A2 value is going to be pi, take away my related acute angle, but my A value is really x plus pi over 2. So that means I've got pi, take away pi over 6, and then I need to move this term over onto the right-hand side to fully isolate my x in order to finish solving my equation. Once I combine those values, I'm going to get a final value of pi over 3. So this tells me right now that I've got a solution of pi over 3, and I also have a solution of minus pi over 3. If I go back to my original domain that I'm looking for, I don't actually want to say minus pi over 3. I want to give a positive answer. So that means that I need to change this negative angle value, which is really just saying this value right here. This is negative pi over 3. I can also write this as 5 pi over 3 because I know that that's the difference between 2 pi and my terminal arm. So my final solutions are that x can equal 5 pi over 3 or x could equal pi over 3. Both of those are in my provided domain. And those are some examples on how to solve trig equations using special triangles and non-special triangles.